Welcome back to The Explainer. Today, we are diving into something truly mind-expanding. We're going to explore Dr. Ahmad Rihan's Dynamic Atomic Model. It's a framework that completely rethinks the underlying fabric of atomic structure, and honestly, it might just hold the key to engineering some revolutionary new materials.
Think about this everyday mystery for a second. Why do elements like carbon and silicon form these remarkably transparent crystals? I mean, you look at a diamond or a window glass, and light just passes right through. What is the specific, hidden structural geometry deep within these atoms that actually allows that to happen?
Okay, let's dive into this. We're going to break this down into 4 parts. First, a new periodic table. Second, the layer shedding mechanism. Third, diamonds, glass, and glow. And finally, predicting extreme new materials.
Section 1. A new periodic table. To understand transparency, we really need to completely rethink how we visualize atomic structure.
So, we're all used to the standard periodic table, right? It groups elements by static electron shells and valence electrons. But the Rihan Modified Periodic Table, or RMPT, flips the script. It introduces a totally dynamic paradigm. It actually visualizes atoms as dynamic Gaussian layered envelopes, and it groups them by orbit completion. In this framework, an element's particle identity actually comes from single quark Euler rotations and Faraday quarters. I know that sounds intense, but it's basically a purely geometric view of the atom.
Now, the absolute key here is a mathematical balance called NMV Equilibrium, or MEE. In the RMPT, MEE happens when the outer electron Gaussian surface and the anti-neutron layers perfectly match the inner proton layers. It's a precise equilibrium. And this exact symmetry is what defines the rightmost column of this new table, the complete orbit column, which, not coincidentally, is exactly where elements like carbon and silicon live.
Section 2. The layer shedding mechanism. This is a really crucial point. Because complete orbit elements have these fully saturated outer Gaussian surfaces, they have a really unique potential for physical transformation. The author notes that under appropriate conditions like extreme temperature or pressure, these outer layers can actually be shed, all while preserving the inner nuclear framework. So instead of just sharing electrons like we usually picture, think of it like peeling an onion. The atom is physically stripping away its outer layers.
Let's move to and see how this builds chronologically. Step 1. When this shedding occurs, it massively reduces the NMV in those outer layers. Step 2. Without them, the atom's effective radius just collapses inward, right toward its central pyramidal body. And then step 3. This sudden collapse is exactly what allows that inner nuclear framework to totally rearrange itself into highly ordered, highly transparent lattices.
Which brings us to Section 3, Diamonds, Glass, and Glow. Let's look at some tangible, real-world results, starting with carbon, specifically C6. According to the RMTP, when carbon completely sheds its outer orbits, its Faraday-Porter orientations are finally able to perfectly align all of its bonds tetrahedrally, and that forms the ultra-hard diamond lattice, without any residual, distorting outer layers getting in the way. So this pure, incredibly symmetric inner framework is the actual geometric causation for a diamond's exceptional transparency and its crazy high thermal conductivity. It's way beyond just a simple electron configuration. It is a literal structural transformation.
And this perfectly mirrors the behavior of silicon, Ci14, which sits right beneath carbon in that same complete orbit column. When silicon sheds its electronic and anti-neutronic orbits, it drastically reduces steric hindrance. This allows it to create transparent crystalline silica and glass with widened effective band gaps. By unifying carbon and silicon like this, the model elegantly accounts for exactly why both of them produce such beautiful, transparent, covalent network properties.
Now, what's really interesting about this slide is how it visually maps out the structural logic of neighboring columns. We just saw how complete orbits like carbon and silicon yield transparent crystals, but look at what happens right next door in the adjacent orbits column. You've got gold, silver, phosphorus, nitrogen. In the real world, these aren't transparent at all. They are exceptionally shiny or glowing elements.
The model gives us a completely fascinating reason for this contrast. Shiny metals like gold have a high free electron density in their incomplete outer layers, and that causes a plasmonic response, giving us that signature luster. Meanwhile, glowing elements like phosphorus have these highly excitable outer layers right on the threshold of completion. These shiny and glowing traits, they aren't just random coincidences, they are direct proof of strong electromagnetic interaction due to slightly perturbed, incomplete orbits. So stepping back, the author argues this dynamic layer completion physics outperforms the traditional periodic table across a few key metrics. It explains allotropes far more deeply through pure geometry. It is highly predictive for materials under extreme conditions. And maybe most incredibly, this exact same layer stripping mechanism unifies with massive astrophysical phenomena, things like neutron stars and Bose-Einstein condensates. It literally offers cohesive physics stretching from the nanoscale all the way to the cosmos.
All right, Section 4, predicting extreme new materials.
Because the true test of any new scientific model is its predictive power, right? Take the extreme heating of zinc, ZN30. The theory maps it out perfectly. Step 1. Extreme heat disturbs that delicate MEE balance. Step 2. This triggers progressive electron and anti-neutron ejection. Step 3. The atom undergoes massive inward shrinkage. And Step 4. Totally novel, transparent crystalline phases actually form. This suggests that using high-temperature furnaces, we could eventually synthesize entirely undiscovered zinc-based glasses or wide bandgap ceramics.
And it gets even wilder. This logic extends to heavier, complete orbit analogs too, like plutonium. Under extreme high pressure and temperature, the RMPP predicts that these heavy actinides will form dense, transparent crystals that exhibit collective, pulsatile oscillations. Think about that for a second. Extreme optical clarity combined with superfluid-like internal migration for heavy radioactive elements. These kinds of sci-fi-esque predictions have absolutely massive potential for next-generation quantum materials.
So, what does this all mean for us? It leaves us with a pretty provocative question. Will experimental verification of these high-temperature zinc and plutonium phases ultimately rewrite our foundational physics textbooks? If shock compression or laser ablation experiments can physically verify these transparent phases, it could spark massive, world-changing breakthroughs in material science. It's a fascinating structural lens for viewing the world, and definitely something to think about the next time you look right through a clear pane of glass.